thank you again for coming. So federated learning is interesting for from different points of view. The first one is that it allows you to train models in a distributed manner. So basically, instead of having the data set in a central point, you spread the data set through a number of nodes, and then you train in those nodes instead of doing it in a central node. This brings a very significant benefit in terms of privacy, because the data does not need to leave the nodes. Okay, so the data is kept on the nodes. No one needs to know about that. And if you are talking about a mobile phone, collecting data about how you use the mobile phone, then maybe users will be more willing to share this data to improve models. This also has the benefit of potentially allowing you to collect a huge amount of data, which will enable to have a better model. Now, how does this work? Okay, so I'm going to give you an overview of federated learning. I'm assuming some of you know about it, some of you don't, so bear with me for one slide so that everybody starts from the same point. So the first thing is you have some central node that has the global model, and this central node might be in the cloud. Okay, so if you're thinking about Google, it's in the cloud of Google. And you have some node over there that initializes the model in a certain manner. And then you have lots of users that will be collaborating in training this global model. So they will have devices. The devices collected data about users, so they have local data sets. This means that these data sets will not be equal in all mobile phones. They will be different, having different characteristics. So this is a depart from the traditional machine learning, because data will not be identically distributed, okay? It will be non-identically distributed. And you want to take advantage of this data. So how can you achieve this? So the first thing is the global model either shares with the subset of devices that will be participating in this round of training, either the seed that initializes the model, or it sends the model to the devices. The devices then train locally using the local data set, and with that they generate a new version of the model, and with that version they can generate an update that is transmitted to the central node, which aggregates all these updates in order to produce a new version of the global model. Okay? Now, this new version of the global model will then again be distributed to a novel set of clients who will produce a new version, and then we'll continue this process until we have a global model that has the properties that we would like. Now, this process can be longer than in the case of a central machine learning, but in the end, it can provide you with the same levels of accuracy, for instance, as if you were training in a single machine. Now, if we think about this sort of organization, you easily think that it's more prone to attacks, because you are talking about maybe a wide area where you have these nodes spread. Also, you are talking eventually about mobile phones, and hackers also acquire mobile phones, and they also can enroll to participate in the training of the model. So it's easy to think that we could have attacks on the nodes. It's easier to have attacks on the clients, but people more recently have also started to consider the case where the central node could also be hacked. Okay, and what can we do if the central node gets hacked? And of course, you could also have attacks on the network. Okay, And the attack will be stronger or less strong, depending where the attacker is located. If it is located near the central node, this means that he or she will be able to see most of the communications and act on them. Or if it's near the client, then probably the attack is going to be much more restricted. Okay? Now, the communications could be on the clear, or they could be protected with, for instance, TLS channels. Okay? So it will depend on your actual deployment scenario. Now, over the years, which is not so many years, so we are talking about 5 years or something like that, okay? But over this period, several variants of federated learning have appeared. So we can think about these variants related to security aspects. So what are the defenses that are implemented? And therefore, you have these different mechanisms in different implementations. What is the scale? And there are two main visions for the use of federated learning. One is what I have already described. We are talking about devices that are together with users. So here we are talking about millions of clients, potentially. But the other scenario that people have been looking at is organizations, okay? So each organization corresponds to one device. So you could think an organization as an hospital that is using the data of its patients to build a global model that is more effective at detecting cancer, okay? So in this case, the hospital does not want to make available the information about the patients, but it would like to take advantage of this data together with the data of other hospitals to have a better model, okay? And in this case, which is called cross-silo, what it means is in each round, instead of having a subset of the clients participating, you will have all clients participating because maybe you are talking about 50 hospitals that will collaborate to build the model. And so you would like also to be able to support this. You have different models being trained. It will depend on the application. And also you will have eventually different data sets, okay? And so people through the years have designed different solutions. And in our case, we are interested in solutions related to security, meaning attacks and defenses. And what we observed is that, first of all these implementations actually were done inside of a single process, although this is a distributed system, so they are really not that realistic. And each person did his or her own implementation, okay? So it means that when I want to test a new attack, I would build my own attack in my emulation of federated learning and implement plus 1 or 2 or 3 to compare, and then it's done. Okay? And then the other person will do something similar, but the implementations will not be equal. The data sets will not be distributed in the same manner. And therefore, when you read one paper and read the other one, it's really difficult to be able to compare the two solutions and understand if one is better than the other. Maybe they are similar, okay? And so this is the motivation that led us to build FADO, okay? So FADO would be something like a framework. I'm calling it an orchestrator. You call it whatever, a platform, where it would be easy to implement attacks and defenses in scenarios for machine learning. In this case, machine learning distributed. In this case, federated learning, okay? And so what are the main principles? The first one is realism. Okay, so if you run an experiment in FADO, you would be able to get results that are comparable to the ones that you get in a real distributed system. The second one is related, so comparable results, realism. So there is some relation between what you observe in FADO and what you would observe in a real distributed system. Scalability, you would like to be able to scale the number of clients, because often you see a limited number of clients participating in the experiments. And lastly, ease of use and customizability, meaning that you could have a user that is not very experienced and he or she could benefit from FADO, and also a more advanced user that wants to produce his own attacks could also customize the execution of FADO in order to be able to develop the attack and experiment with it. Okay? So what is the architecture? Now, the architecture has two main components. The first one is called builder, and the second one is called runner. So the builder is responsible for setting up the system, and basically what it needs to do, it needs to be able to get the data set that you want to use in your experiment, needs to be able to divide the data set by the various clients following a certain policy that you have decided. Okay? So this is one big task, an important task. Now, while you're doing this, you could inject attacks, okay? And attacks here would mean that you would compromise some of the examples. For instance, that would be placed in the nodes corresponding to the malicious attacker clients, okay? And that way, those nodes, when they are used in the execution of the system, they will have, for example, examples that are bad for some reason, okay? Now, when you have the runner has two main sets of components. One is the server, and the other one are the clients. They will have a communication layer. And what we wanted to do here is to have very realistic communication. So I want to have TCP channels. I want to have out-of-the-box TLS channels. Okay, so it should be realistic. And so that's what we actually do. Now, I also want to be able to perform network attacks. Okay, so I have a third entity that I call an interceptor that will act like a malicious router. Okay, so the router sees the packets going through between the server and the clients and vice versa, and therefore the interceptor can act on the packets in different manners. Okay, so if we look inside these entities, so the server has three main modules. One is preparing the global module, the global model that we are training. The second one is being able to evaluate this model using a test set that is provided by the builder, okay, with certain metrics. And the third module is the participant selector that will select the clients that will be used in each round, okay? So you could have something like 1,000 clients, and in each round you select 10 of them, okay? You could use different policies for this selection. The simplest one is you just pick 10 randomly, okay? But you could have much more stricter policies, okay? Then if you go inside of a client, what does it do? It gets the model, it has its own test data, and so it performs local training, and then at the end it returns back to the server the update to the global model based on what was seen locally. Of course, inside the client you can also implement attacks and also implement defenses. So you have modules that implement both operations. And then you send this update to the server. The server aggregates the updates from the 10 clients, let's say. And again, you can have attacks and defenses being applied to the updates. And in this way, you are emulating, for instance, a malicious aggregator a malicious server, or you are emulating a server that implements some defense in order to deal with malicious clients. Okay? So you can substitute those modules over there. And then you produce a new version of the global model and send it back. Now, inside of the interceptor, you have selectors that are able to look at the traffic and using a certain policy decide which traffic should go through and which traffic should be acted upon. And if it's a packet that we want to act upon, you can define actions to be performed. For example, you would like this packet to be delayed, or you would like this packet to have a modification in a certain manner. Okay? The content will be changed in a certain way that you define. Okay? You also have state, meaning that you can take advantage of what you have observed in the past in order to help you decide what you do in the present. Okay? So this is the architecture of FADO. Now, when implementing this, and as I said, this implementation has been going for the past 14 months, one of the main hurdles that we had to deal with has to do with the scalability of the system, because we tried different approaches, and at a certain point you get into bottlenecks. Okay? Bottlenecks can be on your GPU, for instance. So you could remove some of these bottlenecks just by having lots of money and going to Google and say, get me 1,000 virtual machines, okay? But the typical group does not have money to do that. And therefore you need to make very good use of the scarce resources that you have, okay? And so we needed to solve this without increasing the price tag of using FADO. And so we basically tried all options that are available. We started with virtual machines for each client, server, and interceptor. Then we tried containers. Then we tried processes, and it goes on. And I'll show you what is the current solution. But at a certain point, you always get into some bottleneck, okay? Because, for instance, even if you use different processes for each one of the clients, it means that each client will have a PyTorch, for instance, and this PyTorch has a static amount of space that occupies in your GPU, and therefore if you have 1,000 processes, you multiply that space by 1,000 and you have your GPU full, okay? And then you don't have space to do computation, okay? So there is a problem here, okay? So what is the current solution? The current solution is you have one container for the server, one container for the interceptor, one container for the clients, okay? In order to scale the clients, you have one process for all the clients, and each client is a thread, okay? This is the solution that allows us to go as far as we could within a single machine or a few machines, okay? And what we observe is we have memory leakage somewhere, okay, within PyTorch that this solution would not observe, but we observe in practice, okay? And this limits the scale. So we can have 1,000 clients, we can go there, but it's harder to go to 10,000 clients, okay? So we are still thinking if we find a solution for this, but in the meanwhile, what we have done is we created a simulation implementation, a simulation mode of operation of FADO, where you can take advantage of all the things that FADO provides, but everything is run inside a single process, something I wanted to avoid at the beginning. But it's the only manner that we have at this point to scale to, let's say, 10,000 clients or more. Okay? Yeah, please go ahead.
Yeah, so my curiosity is, so FatScale ran into a similar type of problem, and their solution was scheduling, because the consideration is, I don't have to run all the clients concurrently. I just need to have a CDB communication environment, and if I actually have a pool of resources like many GPUs across many nodes, I don't even care about particularly which client runs on which machine at that point. So my question is, would that be a solution for you, or is your security models in this case?
We try to do something like that. Okay, so when you have processes, you actually only need 10 processes in each round. So we killed all the rest of the processes and had only 10. But even though, I don't know if the problem is we are programming this in Python, okay, if it's a problem with the Python library. We haven't gone to C++, okay. We still observed a memory leakage, okay, that was consuming gradually the space in memory of the GPU, and eventually we could not continue the emulation, okay. So it's something we are still working upon. We know more than we knew 3 months ago, but it's still not perfect. Yeah. Okay, how to intercept traffic? How can we do this? Okay, so communications, as I said, are using out-of-the-box TCP. In case you want security, it's again out-of-the-box TLS channels. Okay. And so you really need to act as a malicious routers. And how do you do that? So what we do is we take advantage of IP tables, so at the kernel level, in order to define rules that allow you to select the traffic that goes to application level, to a queue. Then you can act on this packet, send it back to the kernel, which then forwards to the final destination. In order to act on packets, we are using SCAPI to do the changes. So that's the easiest solution we found. Okay? So this is the implementation, the current implementation of the interceptor. Okay, how to allow rapid and customizable experimentation. Rapid means you can define different settings for different things. For instance, you might want to try malicious clients 10 or 15. You can try to attack different classes on your model, class 0, 1, and 9. You define something like this in the configuration file, and then FADO will run the product of all these settings in an automated manner. What about customization? You can define your own modules to do attacks and defenses. And then you just indicate in configuration files, saying, for instance, model attack, it's this Python code. And automatically, when FADO runs, it will use that code to substitute the default module in FADO. Okay, so it becomes pretty simple to substitute one model for another one. Okay. Now, to do a first evaluation of FADO, what we did is we took a recent attack that was developed that did attacks at the network level and at the node level, and we ported it to FADO. And then we compared what we were observing in FADO with the original paper, trying to understand if we could reproduce the same sort of behavior. So let me give you a brief introduction to the attack. So the aim of the attack is to decrease the accuracy of the model in a particular class, your target class of attack. Okay? How do you achieve that? You achieve that by dropping packets in the network. Okay? Which packets are you going to drop? You're going to drop the packets from the clients that are contributing more for the global model to learn how to classify the target class, okay? So you identify these, and after that, you start dropping the packets from these nodes, okay?
You do, quick one, so you do the packet inspection and look for strings?
So, okay, so in their case, so in their case, everything was in a single process, so you have access to everything. In our case, you do that in the interceptor. Okay, so in the intercept, you are able to look at the packets. But in our case, we emulated the version of the attack where the channels are TLS channels. So actually, you cannot see the inside of the packets. So you need to infer this by looking at the global model as it progresses through time, okay? So you have two informations. One is which clients participated in the previous round. Second, you know which version of the model was in the previous round. And then looking how the model evolves, okay, you try to infer if the clients used in the previous round were useful or not to make the model learn the target class. Okay, so this is the aim, okay? Just between me and yourselves, it doesn't work perfectly, let's say it this way. But that's the idea, okay? And I'll show you a few numbers that demonstrate this limitation, okay? Because most of the paper is with channels which are not encrypted. So they see actually the contents of the messages, and in doing things in this manner, they actually can identify well which are the clients that are producing the most interesting updates from the point of view of the target class. When you need to do this by inference, it becomes much harder, okay? And it's much more error prone, okay? So this is a good opportunity for research in the future, okay? They also have malicious clients which poison the model that work together with the network attacker to make the attack more effective, okay? So you cannot read this table, I'm sorry, but it's just to give you an idea. So we have one column of the original paper, one column where we run their code in a local machine, one column where we have FADO implementation, okay? And we have no attack, no defense, target drop, so network attack and no defense, and then I'll show you when you have also no attacks and no defense, okay? Yes?
Just a clarification, so you said your clients are using TLS, right? So
yes.
How can you drop packets in a TCP connection?
How can you drop packets in a TCP connection?
Yeah, if you drop a packet, they will ask for retransmission, right?
Yes, and you drop it again, okay?
But then nothing at all comes through.
Now I need to go deeper inside federated learning. So what does... No, let me explain it, okay? So what does federated learning do? They run into the same problem. They send a request for, let's say, 100 mobile phones, and as you imagine, you will not get 100 responses, okay? So what you do is you send to 130, and when the first 100 arrive, I calculate the global model update, and I'll throw away even if the last 30 arrive, okay? So what you do effectively here is you move the clients that you want to attack to these last 30, okay? And basically you don't let the connection go. And so... I'm dropping packets. That's how I'm implement this in reality, okay? But in fact, you are disconnecting, or you are delaying, okay? You could delay it so the first 100 arrive, and then you let it go, but you already know that it will not be used, okay? So you can play these tricks, okay? Okay, so if you could read these numbers, you will notice that the results that we are observing in FADO are very near to the results that you were observing in the original paper, okay? And then you can start to look at other aspects of the experiment. For instance, depending on the target class that you are attacking, you get different results. Depending on the number of clients that have the target class examples, you also get different results. So as you have more clients with the target class, it becomes harder to do the attack, okay? So there are these sorts of conclusions that you can take. You can also, for instance, conclude that for some data sets, the attack is not very effective, okay? The accuracy decreases slightly, so we are still seeing here 79% accuracy, okay? But for other ones, it can be significant. So here it drops to 14% accuracy. So you are being effective at destroying the target class. Yes?
Sorry, you said that you introduced some malicious clients. In this example, did you drop the packets of real clients and introduce your own malicious ones?
Now, what I do is I select a subset of the clients. These ones are going to act maliciously. But in this experiment, I still don't have malicious clients. It's in the next slide, okay? So here, here I have targeted drop, so dropping packets, plus poison, meaning some of the nodes will poison the model. So send updates to the global model that are being poisoned, okay? And you have the case with no defense and the case where you have some defense, which is norm clipping. I'll explain you in the second presentation in more detail, okay? Now, if you look at this, then when you mix poison attack together with the target drop, you are very effective and you decrease the accuracy in almost cases to 0. Okay, so you can really kill the target class. Okay, now if you add defenses, then this is no longer true. So norm clipping, which is what they were using, is actually for several of the cases quite effective at preventing the attack. Okay, so you can look here, and if you could read, you have cases where the accuracy is 0, so the attack continues to be effective. But then you have cases where the accuracy it's 56%, 61%, etc. Okay? Thank you.